Hello everyone. Hope you are doing very well. As you all know that today we are going to cover the theory part 4 of the chapter coordination compounds. So let's begin our today's topic, that is NCERT chapter 4 coordination compounds theory part 4, and today in this lecture we are going to cover the NCERT section 5.4.5 to 5.5.1. This is disclaimer. So today's lecture objective. So after attending this lecture, you will be able to understand the nature of bonding in the coordination compounds in terms of valence bond theory. And what are the topics that we are going to cover today? According to the NCERT, the first section is 5.4, including isomerism in the coordination compounds. Then 5.4.5, the ionization isomerism. Then 5.4.6, including which is Solvate or Hydrate isomerism. Then we will study about the section 5.5, that is bonding in the coordination compounds. Then we will cover our next subsection 5.5.1, that is valence bond theory. So let's begin with the isomerism and the coordination compounds. So the isomers. So isomers are the two or more compounds that have same chemical formula but different arrangement of atoms. That we have understand this already, that isomers are those compounds, either two or more than two, which have same chemical formula but their arrangement of the atoms in the 3D space are different. They differ in one or more physical or chemical properties. So due to this different arrangement of atoms, they differ in one or either more than one physical or chemical properties. So they will show different physical and chemical properties. The two principal types of isomerism are known, which can be further subdivided. How? So the one of the principal type of isomerism is stereoisomerism. Under this can be further subdivided into geometrical isomerism and optical isomerism. We have covered about this in our previous lecture. The second principal type of isomerism is structural isomerism, which can be further divided in linkage isomerism, coordination isomerism, ionization isomerism, and solvate isomerism. Okay, so today we are going to cover the two types of isomerism which comes under the structural isomerism, the ionization and the solvate isomerism in detail. So let's begin with the first type of isomerism with subsection 5.4.5, that is ionization isomerism. Now this is a type of structural isomerism in the coordination compounds. Okay, so ionization isomerism is shown by the coordination compounds having like different structure. So this is a type of structural isomerism. It happens when a counter ion swaps the places with a ligand inside the coordination sphere. So when you observe the ionization isomer in a coordination compound, when inside the coordination sphere, that means the square bracket enclosed thing, so when inside the coordination sphere a counter ion will swap the place with the ligand, then the ionization isomerism occurs. We will understand. So the key points include having they have same formula and different ions. That means the ionization isomers have same overall chemical formula if you write for a coordination sphere, but they are going to produce different ions when they dissolve in the solution. Okay, due to the swapping of this counter ion with the ligand, that means the swapping between the counter and the ligand, we have the occurring of this ionization isomerism where they are having overall similar chemical formula, but when they dissolve in water or solution, they produce different ions. Ligand exchange. So an anionic ligand within the complex and an anion outside the complex, which is called as the counter ion, exchange the positions and the counter ion must be able to act as a ligand itself. So there is a key point or a property that a ligand exchange happens here. How? So an anionic ligand means the ligand having overall negative charge. So when an anionic ligand within the complex is present, and an anion which is present outside of the complex, outside of the square bracket, and we also call this outside ion as counter ion. When they both exchange positions, the anionic ligand and the anion which present outside of the complex called as counter ion, when they both exchange their positions within each other, the counter ion must be able to act as a ligand itself. So this happens in this ionization isomerism, and there is this thing that this only happens when the counter ion is able to act as a ligand itself, so that when it goes or when it swaps the position with the anionic ligand, the counter ion will going to act as ligand within the complex. Okay, so the counter ion must be able to act as a ligand. Let's understand this concept by using the examples. So first example is this complex having cobalt as the central metal, NH3-5SO4, they are the ligands, and the counter ion is bromine here in this complex. Now sulfate SO4 negative ion is a ligand here, right, because it is present inside of this coordination sphere, and the bromide, that is Br negative, is the counter ion because it is present outside of the square bracket, right, as per the definitions of ligand in the counter ion. Now when dissolved, so when you dissolve this complex, it releases bromide ions in the solution, because as per the property of the counter ion can be separated from the complex structure when it is dissolved in the solution. Meanwhile, the structure of the complex, the coordination sphere, is going to be remain intact. So when you dissolve this complex in the solution, it is going to release bromide ions, because bromide ions are the counter ion, or is the counter ion present in this complex. So second example you can take is cobalt ammonia whole 5 bromine sulfate, right? Here if you see, the complex is same, only bromine here, which is the counter ion in the first complex, change or swaps its position with this anionic ligand SO4 negative, 2 negative, right? So here SO4 comes outside of the coordination sphere and become a counter ion. Meanwhile, this bromide, which was the counter ion, now swaps the position with the ligand and becomes a ligand here. So here the bromide is now the ligand, and the sulfate ion is the counter ion present outside of the coordination sphere. And when it is dissolved, this complex is dissolved in the solution, it is going to release the counter ion, which is sulfate in this case. Let's see our next type of isomerism, that is let's cover the next subsection 5.4.6. So this is a solvate, or you can also call it as hydrate isomerism. So a type of structural isomerism in the coordination compounds. So this is also comes under the type of structural isomerism, okay, which is observed in the coordination compounds. Now the isomers which are differ based on whether a solvent molecule is directly bonded to the central metal ion as a ligand, or present as a free molecule in the crystal lattice, or it is based on the number of water or the solvent molecules which are acting as a ligand. Okay, so try to understand this definition, that isomers differ or are different from each other based on the concept that whether a solvent molecule, that means either water molecule, is directly bonded to the central metal ion, or you can also say either it is present as a ligand or it is present as a free molecule in the crystal lattice. That you have to like observe between the two different, or between the two isomers, to differentiate between them. Okay, so solvate isomerism is observed when the two isomers are different from each other on the basis of that whether inside those complex or isomer, a solvent molecule is directly bonded to the central metal ion. That means either it is acting as a ligand or it is present as a free molecule in the complex, in the crystal lattice. Okay, or you can also like observe the difference between the isomers by seeing that the number of water or the solvent molecules are acting as a ligand or not. Okay, so ligand has this property of directly connecting with the or bonding with the central metal ion with coordinate covalent bond. So that's why we are saying that if our solvent molecule is present as a ligand, that means it is directly bonding to the central metal ion, or it is present as a free molecule in the crystal lattice. Then you can differentiate between the two isomers. Okay, and also it is based on the number of water or the solvent molecules which are going to act as a ligand present in the complex. So hydrate isomerism. Now let's talk about the hydrate isomerism. So a specific case of hydrate isomerism is a specific case of a solvent isomerism where the solvent is water. Okay, so in the solvent isomerism we cover every solvent including water also, it can be water. But in the hydrate isomerism, because it is a specific case of the solvent isomerism, in this the solvent included is only water, that is H2O. This is the most common form of solvent isomerism we observe. Okay, so this is the like most common form of solvent isomerism. That means mostly if you observe the solvent isomerism, in that mostly the solvent molecule is going to be water. Okay, so that's why we are calling here solvent hydrate isomerism. Let's see some key points in this topic. So same empirical formula. Now what it is saying that all the solvent isomers will have identical empirical formula. So we are saying that in the solvent isomerism, the solvent isomers, which are different from each other on the basis of the number of molecules of solvent molecules, so basically all those solvent isomers will going to have the identical or same empirical formula. Okay, ligand exchange, the next second major key point, that often involves an exchange between a solvent molecule which is acting as a ligand and an anionic ligand which is present outside of the coordination sphere, or vice versa. Okay, so in the solvent or hydrate isomerism we observe these two key points. First, that all the solvent isomer is going to have the same identical empirical formula, and the second point is that ligand exchange. That means it often involves an exchange between a solvent molecule which is acting as a ligand and an anionic ligand which is present outside of the coordination sphere, or you can say vice versa, like an ionic ligand is exchanging the solvent molecule present as a ligand, or either the that like when an ionic ligand is going to be inside of the coordination sphere, then the second case will cover. Okay, that it is going to replace the place of the outside ligand that is going to be present in the second case. Okay, so ligand exchange can happen in the solvent hydrate isomerism between the solvent molecule acting as a ligand inside the coordination sphere and the anionic ligand present outside the coordination sphere, or vice versa. And also the solvent isomers are going to have the same empirical formula. Let's understand this concept by using an example. Let's take chromium plus 3 aqua complexes. So this is chromium plus 3 aqua complex. Okay, hexa aqua basically. So chromium H2O whole 6 Cl3, which is violet in color. So it represents the violet color, this complex. You can observe that all the 6 water molecules are coordinated ligands here, right? The ligands which are present in this complex are water molecules, which are 6 in number, right? So we have studied that solvent or hydrate isomerism include when the ligand is going to be like a solvent molecule or a water molecule. Okay, here you can easily observe that all the 6 ligands are water molecules that are coordinated ligands present in this complex. Now all three chloride ions are counter ions. This thing you can clearly differentiate that three chloride ions are present outside of the coordination sphere. That means they are counter ions, right? Second, chromium H2O whole 5, chlorine, Cl2 dot H2O. Now this is the another complex which is a solvate isomer of this first complex of violet color. Now this second structure or second formula of this complex is the complex show gray green color. So, okay, so it indicate the different color indicate that this complex is going to be different from this first one. Their empirical formula, that means the formula in which the number of all the atoms, the constituent atoms making this coordination compound is representing, that will be same, that will going to be same, but the arrangement, if you observe in the two complex structure, that's going to be different, right? What is the difference? So here if you observe in the second complex, the central metal is same, chromium. Now one of the ligand of water molecule is replaced or is swapped by one chloride counter ion, right? So here the chloride counter ion from 3 decreased to 2, and here the water molecule from 6 decreased to 5, because one water molecule is swapped its place with the one chloride counter ion. So that chloride counter ion is going to now present as a ligand inside of the coordination sphere, and that water molecule that swaps the place with the chloride ion is going to be act as a counter ion this time, or a free ion present in this complex. So here 5 water molecules and 1 chloride ion are going to be our coordinated ligands, and 2 chloride ions are going to be our counter ions, and 1 water molecule is a free solvent molecule present in our crystal lattice. So that is the main difference between these two, that their empirical formula is going to be same, but their arrangement is changing, and they are showing solvate or hydrate isomerism, right? By showing that yes, one of the ligands swapped its place with the one of counter ions, and the counter ion become the coordinated ligand, and the ligand becomes either the counter ion or present as a free solvent molecule in the crystal lattice. Okay, let's see the bonding in the coordination compounds, our section 5.5. So we have covered the Werner's theory. Now let's see the limitations of Werner's theory. So Werner was the first to describe the bonding feature in the coordination compounds, but there are some limitations of the theory given by him. Okay, so first is that why only certain element possesses the remarkable property of forming coordination compounds. The first question asked after the Werner theory is that why only certain elements are there which possess this property of forming coordination compounds. Second question or second limitation is that why the bonds in the coordination compounds have directional properties. Remember, we have studied about the primary and the secondary valence showing directional or non-directional properties. So here the Werner theory was unable to explain that why the bond in the coordination compound have this directional properties. The third limitation includes that why the coordination compounds have characteristic magnetic and optical properties. So because it was given that the coordination compounds show their own magnetic and the optical properties, but why is it so? Why the coordination compound have their own characteristic magnetic and optical properties, that doesn't explain by this Werner theory. So these are the three limitations which is present here, right? So Werner obviously was the one to describe the bonding, or he was the first to describe the bonding features present in the coordination compound, but he was not able to explain these three major limitations. Now, explanation of the nature of bonding in the coordination compound is given by various theories. One was Werner theory, right? So explanation of nature of bonding, that are bonding which are going to be present in our coordination compounds. What is going to be its nature, the nature of bonding? It is explained by various theories. Like the first theory includes Valence Bond Theory, VBT. We commonly called it as VBT. The second theory is crystal field theory. Okay, this also explains the nature of bonding present in the coordination complexes. Third is ligand field theory. This is also helpful on explaining the nature of bonding of coordination compounds. And the fourth one is molecular orbital theory, commonly known as MOT, right? Let's talk about the valence bond theory first, that is VBT. Okay, so this is subsection 5.5.1, the valence bond theory. So this theory provides a framework to understand that how the central metal atom or ion in the coordination compound forms the bond with the ligands. Okay, the bonding that are involving within the coordination compound between the central metal atom or ion and the ligand or the anions that are surrounding, or the neutral molecules that are surrounded the central metal atom or ion. Okay, so the bonding that are forming between those two those two molecules, the central metal atom or ion, or the anionic or neutral molecule surrounding the central metal atom, the bonding that is forming between those, the nature of that bonding is explained by the valence bond theory. So this theory provides a framework to understand this nature of the bonding. It focuses on the overlap of orbitals to create a stable bond and predict the complex's geometry. So valence bond theory is mainly focused on the orbital overlapping. Okay, so how different orbitals s, p, d, f. Okay, so if possible in those orbitals, the overlapping of orbital, then this theory is going to describe that. Okay, so this theory focuses overlapping of the orbitals to create the stable bond between the central metal atom and the ligands, and to predict the complex geometry that is going to be. The first factor we are going to focus on is availability of empty orbitals. So for the overlapping, there should be the availability of empty orbitals in the element. So under the influence of approaching ligands, central metal atom or ion prepares a specific number of empty orbitals. Okay, so because the central metal atom or ion want to form the bond with the ligand to make a complex structure or a stable complex structure, right? So that's why we are saying under the influence of approaching ligand. The approaching ligand means the ligands which are coming to make the bond with the central metal atom. The central metal atom is preparing itself by a specific providing a specific number of empty orbitals for the proper overlapping of orbitals between the ligands and the central metal atom or ion. The number of empty orbitals made available by the metal is precisely equal to its coordination number. Now here is this concept that the central metal atom is going to prepare itself for providing the empty orbitals for the approaching ligands toward itself, right? Now what will be that number of or empty orbitals that will be made available by the metal? That this is precisely equal to the coordination number of the, you can say, metal. Okay, then that means the number of ligands that are directly attached to the central metal. Okay, so coordination number we have studied that it is determined by the number of the ligands that are going to surrounded the central metal, that determine the coordination number. And the number of empty orbital which will going to be provided by the metal is precisely equal to this number, coordination number. These empty orbitals can be a combination of its s, p and d atomic orbitals. Okay, now this empty orbitals which the metal is going to be made available, this can be the combination of either s, p and d atomic orbitals, the different orbitals. Okay, the combination of orbitals will also can be made available by the metal as the empty orbitals. Second point to focus is hybridization for defined geometry. These empty metal orbitals that are provided by the metal then undergo the hybridization process. This means that they are going to mix together to form a new set of equivalent hybrid orbitals. Okay, so what we are saying here, that hybridization is going to happen. Okay, hybridization is going to happen between those like empty orbitals, empty metal orbitals. So they undergo the hybridization process. What does that mean? That they are going to mix together to form a new set of equivalent hybrid orbitals whose energy is going to be equivalent to each other. So orbital hybridization is basically something that is the mixing of, this is the mixing of atomic orbitals to form the new hybrid orbitals. Okay, so the empty orbitals which is provided by the metal, that are going to intermix with each other to form a new hybrid orbital which is suitable for the pairing of electrons to form the chemical bond with the coming ligands. Okay, so that's why the empty metal orbitals will undergo the hybridization process for the availability of the pairing of the electrons to form the chemical bond. And this is going to like these empty orbitals after the hybridization going to mix together and form a new set of equivalent hybrid orbitals for the better formation of the chemical bond, or for the better bonding with the ligands upcoming. These hybrid orbitals are crucial. Why? Because they are directed in the space with a definite geometry, which determines the overall shape of the coordination complex. So the hybridization is very important, because when the orbitals will going to hybridize, that means when they are going to mix together. Okay, that means when the atomic orbital mixing will happen, what they are going to create, they are going to create a new set of equivalent hybrid orbitals, the hybrid orbitals for the availability of pairing of the electrons for the easy bonding. And these hybrid orbitals are very crucial, very important, because they are directed in the 3D space having definite geometry, and this definite geometry is going to determine the overall shape of our coordination complex that are going to form. Okay, so this hybridization is the main thing or the main cause to which our complex compound geometry is going to be like affected, okay, or determined, you can say in both way. The type of hybridization directly corresponds to complex geometry and coordination number, as shown in the table below. Now we are going to see a table where it is clearly shown that what is the type of hybridization, and this type of the type of hybridization shown by the complex will directly related to the complex geometry and the complex coordination number. How? Let's see in the table. So let's see the table 5.2, which is showing the number of orbitals and the types of hybridization. So in this table you can see we have 3 columns: coordination number, types of hybridization, and the distribution of hybrid orbital in the space. So if the coordination number is 4, what does that mean? That if the number of ligands that are approaching towards the central metal atom for the bonding are 4, the type of hybridization is going to show is sp3. That means one s orbital is going to intermix with the 3 p orbitals to form the equivalent hybrid sp3 orbital. Okay, and they are going to directed in space, they are going to present themselves in the space with a definite geometry, and that geometry is going to determine the coordination complex geometry. So that is going to be, so the distribution of hybrid orbital in the space is tetrahedral in the case of sp3 type of hybridization. 1s 3p, if you go on the like diagram or the 3D structure of each orbital, then you can understand more better that how s orbital is going to, what is the shape of the s orbital in the 3D space, what is the shape of the p orbital in the 3D space, how they are going to like intermix together to form the tetrahedral distribution in the space. Okay, that is, then we are then you are going to understand more. So so for now if the coordination number is 4, that means 4 ligands. If the 4 ligands are approaching towards the central metal for bonding, the type of hybridization they will show is sp3, and the distribution of these hybrid orbitals in the space is going to be tetrahedral geometry, is going to have tetrahedral geometry. Now similarly, the second case possible is that if the coordination number is 4 again, that means 4 number of ligands, but here the type of hybridization changes from sp3 to dsp2. 1 d orbital, 1 s orbital, and 2 p orbitals are going to intermix together. Then they are going to distribute themselves in the space. The hybrid orbitals are going to distribute themselves in the space in the form of square planar geometry. Okay, here also, like, you have to understand the geometries more specifically, that how each geometry is going to be present in the 3D space. Okay, how tetrahedral is arranged, how square planar shape is. Okay, so when the atomic orbitals are going to mix to form the new hybrid orbitals with the different energies, because s is going to have different, d is going to have different energy, right? So when these atomic orbitals mixing will going to happen to form the new hybrid orbital with different energy, shape, and the orientation, because they are going to orient themselves in different directions. So why they are doing that? For the definite bonding, for easy bonding with the upcoming ligand, right? For between the central metal ion and the ligands. Okay, and the geometry or the distribution of these hybrid orbital in space, and they make this a definite geometry after spacing themselves in the like space, or after placing themselves in the space, they are going to show a definite geometry which is going to determine the coordination complex geometry. Okay, so if the coordination number is 4 and the type of hybridization is sp3, that means 1s orbital combines with 3p orbitals, then in the space, if it is going to distribute themselves in the tetrahedral shape, then this tetrahedral shape is going to be the shape of our coordination complex. Okay, similarly, if the coordination number is 4 again, but this time the type of hybridization is different, 1d orbital, 1s orbital, and 2p orbitals are going to be like participate in the hybridization. Then if the distribution of hybrid orbital in space is square planar, then this is going to be the shape of the complex, square planar. Similarly, if the coordination number is 5 and the type of hybridization included is sp3d, that means 1s orbital, 3p orbitals, and 1d orbital are going to intermix together under the hybridization process, and then they are going to place themselves in the space, or then the distribution of hybrid orbital in space is going to be trigonal biapyramidal. Okay, now if the coordination number is 6 and the type of hybridization is sp3d2, that means 1s orbital, 3p orbital, and 2d orbital is going to intermix. The distribution of hybrid orbital in space will going to be octahedral. And if the coordination number is same like 6, but the type of hybridization changed by d2sp3, 2d orbital, 1s and 3p, okay, then the distribution of hybrid orbital in space will again going to be octahedral. Okay, so this is the table like which is showing the type of hybridization which are directly corresponding to the complex geometry and the coordination number. Okay, so these are the geometries that are going to be present for these hybrid orbital distribution in the space, and that are going to reflect the geometry of the complex compounds, right? Third major point is that formation of coordinate bonds. So the ligands which act as Lewis bases possesses lone pair of electrons in their orbitals. Okay, so coordinate bonds means the central metal ion and the ligands are going to form the coordination covalent bond, right? Coordinate covalent bond. And the ligands that are bonding, they are going to act as Lewis bases. Okay, and they possesses lone pair of electrons, so they are going to donate those electrons to the empty orbitals of the central metal ion. Okay, so ligands are going to act as Lewis bases having lone pair of electron in their orbitals. Now these electron donating ligands orbitals then overlap with empty hybrid orbitals of central metal atom or ion. Okay, So these electron donating ligand orbital is going to overlap with the empty hybrid orbitals of the central metal atom, and this overlapping between the ligand and the central metal empty orbital, this overlapping leads to the formation of coordinate covalent bonds or dative bonds, where the both electrons in the shared pair are going to donated by the ligand to the metal. Okay, so this overlapping between the orbital of ligand and the empty orbital of central metal atom or ion leads to the formation of this complex covalent bond or dative bond, which forms when both the electrons in the shared pair in the bonding, including the two electrons in the shared pair, they are donated by the ligand to the metal. Okay, let's see the classification on the basis of hybridization. Okay, how can you classify the complex on the basis of the hybridization? The first is inner orbital complex. Okay, we also call it as low spin complex. So in the inner orbital complex, this uses n-1 d orbitals, so second last energy levels. Okay, so it uses n-1 d orbitals. This is a table showing the hybridization for a corresponding coordination number. So if the coordination number is 4, the hybridization is going to be dsp2. If the coordination number is 6, the hybridization is going to be d2sp3. Okay, so second type of complex is going to be existing as outer orbital complex, or you can also call it as high spin complex. They uses nd orbitals. That means the electrons that are present in the n or last energy level of d orbital, that electrons are going to be used by the formation of this outer orbital complex. So they will show this type of hybridization of the coordination complex with this coordination number, which is shown in the table. So coordination number is 4, where hybridization is going to be sp3, and when coordination number is 6, the hybridization of complex is showing to be sp3d2. Okay, so they like this table showing the coordination number or the hybridization corresponding to the coordination number, and these type of and the complex that are going to form using these two or exhibiting these coordination number having these hybridization is going to form the outer orbital complex. Similarly, this table under the inner orbital complex showing the coordination number, or you can say hybridization corresponding to the coordination number given, and which are going to form the complex that comes under the inner orbital complex. So let's first study about the inner orbital or low spin complex. First of all, they form octahedral complex. That means their coordination number is going to be 6. That means they can have 6 vacant sites at which the ligand can attack and form the bond. So this is the diagram you can see showing the orbitals of cobalt 3 positive ion. So we are taking here example as cobalt 3 positive, where 3d orbital is given having 6 number of electrons in it, in which 2 are paired, other 4 are non-paired or unpaired, and the 4s and 4p orbitals are represented alongside for the hybridization purposes. Now this the coordination number is 6. So d2sp3 hybridized orbital of cobalt 3 positive will going to show the configuration as, so we have like pairing will happen in these unpaired electrons, and this diagram of the orbital will become like this. So this electron will go here with the one unpaired electron, and this unpaired electron will go here and with the another unpaired electron. So 4 unpaired electrons is going to be paired, and 2 paired pair is going to be obtained like this. Okay, so and 2 orbital of this 3d 2 this energy level, 2 energy level, or you can say 2 boxes of here 3d orbital is going to be empty, because these 2 spin or these 2 electrons are going to be paired up with these 2 electrons, right? So these 2 boxes or energy levels inside the 3d orbital is going to be empty. right? So that will going to like include with the 4s and the 4p orbitals to form the d2sp3. That means two boxes of two energy levels of this 3d. One is from s and 3 is from 4p, that we are taking as a hybrid to, for the like proper uh, ligand bonding, because its coordination number is 6, so 6 ligands can attach to it, filling their electrons in these energy levels. So for this complex cobalt NH3 whole 6 whole 3 positive, the ammonia are ligands. Okay, they are coordinated ligands in 6 number, so its coordination number is 6 already. And this is going to be inner orbital or low spin complex. The configuration for 3D is going to be this one, and the 6 pair of electrons from the 6 ammonia ligands are going to be filled in this D2sp3 hybrid empty orbital or hybrid orbital of the central metal ion, that is cobalt. Okay, so like this 6 pair of electron from the 6 ammonia is going to be filled here, which is showing that yes, around the central metal ion cobalt, the 6 pair of ligands of ammonia is going to be arranged themselves, and it is a inner orbital or a low spin complex. Okay, so this is using n-1 d orbital. N-1, why? Because the n is 4, n-1 is 3, and it is using the 3d2 orbitals here for the hybridization, so that's why we say. And this is a low spin complex, it doesn't have any unpaired electron in it. Okay, so if you want to see the explanation for this cobalt NH3 whole 6 3 positive, so cobalt is going to be the central metal ion, and it is present in its +3 oxidation state, and strong field ligands of ammonia is present in this complex, right? So ammonia is a ligand which is a strong field ligand which is present in this complex. Strong field ligand, that means it will it will prefer pairing, so it will do the pairing of the electrons. So 2d, 1s and 3p orbitals, like from this, after pairing 2d, 1s and 3p orbitals will going to be hybrid, that will going to intermix together, and the ligand will going to donate the electrons in these empty hybrid orbitals. Okay, hence the hybridization will going to be d2sp3 with the octahedral geometry. So the outer orbital or high spin complex, where the octahedral complex having coordination number 6. If you observe this in the another example of the complex cobalt F6 whole 3 negative, where cobalt is the central metal or ion having atomic number 27, the 3D configuration will be 3d7, and the arrangement of electrons is like that in the 3d orbital. In the 4s, 2 electrons is going to be present, so 3d7 4s2, and 4p is going to be empty. Now cobalt here is having +3 oxidation state, so the 3 electrons are going to be donated by the cobalt. So 2 electrons will go from 4s and 1 electron is going from 3d7, so it will remain as 3d6, right? Now for the cobalt F6, the 6 fluorine ligand are going to be coming towards the cobalt to form the bond, and it is going to form the bond and going to donate its electron in these empty hybrid orbitals. 1 is from 4s, 3 is from 4p, and 2d is from the another d orbital. Okay, so if you see the explanation for this complex cobalt F6 whole 3 negative, the cobalt here is in +3 oxidation state, so weak field ligand, that is fluorine, is present here. So fluoride ion is a weak field ligand. Okay, that means in the presence of weak field ligand, there is no pairing of electron will going to happen. So there is no pairing of electrons, due to which these electrons which are unpaired already in 3d6 are going to remain unpaired. Okay, so only 1s from 4s, 3p from the 4p, and 2d orbitals will going to hybridized, will going to undergo the atomic orbital intermixing, and the ligand are going to donate its electron in these hybrid empty orbitals. So the hybridization here in this case is sp3d2. Okay, you can see that in the outer orbital complex, nd electrons are participating, right? The electrons which are occupying by the n, that is 4 in the d orbital. Okay, thank you so much. That's all for today's chemistry session. Thank you.